Good morning, welcome back. Last class we proved the Wald's equality, which talks about the expected value of a, which relates the expected value of a stopping time to the expected reward at stopping, right. We will now head towards proving the elementary renewal theorem. Just to refresh your memory, I have stated this somewhat informally before. The elementary renewal theorem says that if n t is a, let n t be a renewal process with average inter arrival time x bar. This x bar could be finite or infinite. Okay. Then limit t tends to infinity, expected n t over t is 1 over x bar. Okay. This is the result that we want to prove. Proving this involves stopping times and Wald's equality in a crucial way. Okay. We have already said that this elementary renewal theorem is not a direct consequence in any way of the strong law. Okay. N t over t of course almost surely converges to 1 over x bar, but if you take expectation there is no guarantee that it will converge to 1 over x bar, right. I mean MCT and DCT do not apply, you cannot apply monotone convergence or dominated convergence. So, but there is a route through Wald's equality. Okay. Proof. So, we need a stopping time for S n. Okay. Okay, this is what we will first define. Okay. So, you are basically getting these realizations of xi's, right. When your renewal process evolves x1, x2, x3 etcetera realize. Okay. Now, you fix a t. So, this is the first step, stopping time for S n greater than t. Fix any t greater than 0, let j be the first index n such that S n is bigger than t, right. So, what do I really mean? J is defined as the smallest n such that S n has strictly exceeded t. So, my random variables S1, x1, x2 etcetera are realizing, from which I make these partial sums S n, right. Each time a new xi realizes, I will form the partial sum, right, and ask. So, I am fixing t ahead of time. Okay. You fix whatever t you want, finite t greater than 0, and ask what is the first index n for which my S n strictly exceeds t. Okay. And that is my definition of j, alright. So, I can just as well write this as minimum n such that sum over I equals 1 through n x I greater than t. So, this j functions like a stopping rule for these x i's. Okay. So, for each n I will add up the first n x i's and t is anyway fixed. I will ask the question, is my x I, is my sum over x I greater than t, right. The answer will be no, 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 and suddenly an s, right. The moment I say yes, I call that n as j. Okay. That is my stopping rule. I am not looking ahead, right. I am just looking at whatever x i's realize. I look till then and see if my sum exceeds t. If not, I continue. If it does exceed t, I stop, right. So, this is a valid stopping rule. In particular, you can see that the event this j greater than or equal to n is independent of x n plus 1, x n plus 2 etcetera. correct. So, this is my stopping rule. Okay. Now, I want to express, at this point it is not even clear how I am going to get to elementary renewal theorem, but just hold on for a minute. Okay. I am just going to see what this j is in terms of n of t. Okay. So, what do we have, right. So, I have this j minus 1, j minus 2 are all such that, right, this will hold, right. This is true for s j minus 1, s j minus 2 etcetera will be less than or equal to t, but s j should be greater than t, right. This is just from the definition of j. Till j minus 1 I should be less than or equal to t, s j minus 1 should be less than or equal to t, s j should be bigger than t, then you stop, right. So, clearly now this should give you a sense of what j ought to be in terms of n of t. Just let us just draw this picture. A bunch of renewals running, okay, this is 0. At some time t, what is the arrival before t? S n t, right. This we know from before, correct. There have been n of t arrivals at time t. So, the previous arrival was epoch was S n t and the next arrival epoch is S n t plus 1, this we already know. So, in terms of S j, what did we say? S n t is basically S j minus 1 and S n t plus 1 is S j, right. So, what are we saying? So, we are basically saying that from the picture it is clear that, right, j is n t plus 1, from the picture it is clear. So, the first index that I know exceeds t is the index n t plus 1 for every t, right. So, the stopping rule j is nothing but n t plus 1, it is very clear from the picture. So, n t plus 1 is the stopping rule for the first index that exceeds t, n t is not a stopping rule, that is the key issue, because at n t if I am just here, right, if I just look at the random variables x 1 x 2 etcetera till x n t which leads to s n t, I have no knowledge of whether there will be an arrival before t or after t, I cannot say, right, whether at this point as s n t epoch I will not be able to tell whether the next arrival will be before t or after t, that I cannot decide without looking ahead, right. But at s n t plus 1 I know that I have exceeded t, right. So, n t plus 1 is a stopping rule, okay. And is this finite with probability 1? For every t n t is finite. So, j is finite with probability 1 and expected n t is also finite, correct. So, expected j is finite, correct. So, we can invoke Wald, right. Note that expected j is equal to expected n t plus 1 is finite for all t by Wald. We get, what do we get? Expected S j is equal to x bar times expected j, right. Yeah. So, now I can put, but I know what j is, right. So, I get expected S n t plus 1 is equal to x bar times expected j which is expected n t plus 1, correct. Okay. So, this equation is important, this is true for all t greater than 0. So, what have I done? I have just invoked Wald's equality for the stopping rule j is equal to n t plus 1. So, you can see that there is some expectation of n t is emerging right here. So, I can rearrange this. So, I want to deal with this, right, expectation of n t I can write as, can you help me out here, expectation of Snt plus 1 over x bar, correct, minus, this is true for all t greater than 0. Okay. What I want is expected NT over t as t becomes very large, correct. So, expected NT over t is equal to expected SNT plus 1 over Tx bar, correct, minus 1 by sorry. So, sorry I think minus 1 over t with me. I hope my algebra is correct. Okay. Now, I want to send, I really want to send t to infinity, but I do not know how to control this term expected NT plus 1 SNT plus 1 sorry expected SNT plus 1, okay, correct. So, now see one direction is very easy. So, if I want to prove that the limit of the left hand side is equal to 1 over x bar, I basically want an upper bound and a lower bound on the left hand side. Okay. It turns out that the lower bound is actually quite easy. Okay. So, let us look at the lower bound. See, we know that strictly greater than t for all t, right, always the case. You can go back and look at the picture if you want. SNT plus 1 always occurs strictly before, strictly after t. Thus, expected SNT plus 1 is greater than t, right. So, the right hand side, so I have the following, right. So, expected NT over t is equal to all this, right, but I can say is greater than or equal to t over T x bar minus 1 over t. What have I done? I have just, see, if you look at this term. So, if you just look at this term, right, that I am saying is bigger than or equal to t, actually it is bigger than t, right. So, I can just actually I can write bigger than here, right, I can confidently write bigger, right, not just bigger than or equal to, correct. I am just putting a lower bound, of course, I have a cancellation here, t is greater than 0, right. This is equal to correct. So, what do I have? I have expected NT over t is strictly greater than 1 over x bar minus 1 over t. So, if I take limit expected NT over t should be greater than or greater than or equal to. See, basically what I have is expected n of t is strictly greater than 1 over x bar minus 1 over t for all t. If I send t to infinity, greater than will become greater than or equal to, right. It is like this, right, 1 over n is strictly greater than 0, but if you send n to infinity, the limit is greater than or equal to 0, you cannot say is strictly greater than 0, right. So, this I will get is greater than or equal to limit t tending to infinity of the right hand side, which is this guy goes to 0, right, 1 over t goes to 0, right. So, you will just get 1 over x bar. So, lower bound is done. So, whatever this limit is greater than or equal to 1 over x bar. I want to prove equal to 1 over x bar, right. I have proven greater than or equal to 1 over x bar. Okay. See, the upper bound is a little more tricky, okay, because so I want an upper bound. So, I want an upper bound on expected SNT plus 1 minus t, that is what I got, right. So, I want an upper bound on this bit, this is what is SNT plus 1 minus t, right. I want an upper bound on this expectation. Okay. Now, this is basically I want an upper bound on the expected value of the residual time, what we have already talked about as the residual time, but we know that the expected residual time depends on the second moment of x, right, which could be infinite. I have not made any assumptions about it, right. So, I may not be able to directly bound it, correct. I have not said that second moment is finite or any such thing. So, in fact, I should be able to prove elementary renewal theorem regardless of the second moment being finite or infinite. In fact, even I am allowing x bar to be finite or infinite, correct. So, it is not clear directly how you bound this expected SNT plus 1 minus t, upper bound this guy. So, it is a little more involved, okay, but it is one of those we can use a standard trick in probability, which is to if something can be unbounded, what do you do? The standard trick in probability is to truncate the random variables, okay. Some of the most important theorems in probability, including the laws of large numbers and all that, they are at some point you truncate, right, to control things. So, truncation trick, okay. Define xi tilde as min or max, min of xi comma b, or maybe I should say max, right. I am truncating, I may not. So, what, so I want it to be, sorry, I want it to be xi when xi is smaller than b and b when xi is bigger than b. So, I should put what I put was right, I always have this confusion, right, min or max, okay. So, this is good, this is what I am defining, and likewise I define Sn tilde is equal to sum over xi I is equal to 1 to n of the tilde variables, okay. So, you are like considering a new renewal process, okay, this tilde process where your xi tildes are equal to xi, but if xi becomes very large it becomes b, xi is become b, and likewise the Sn tilde is defined as the sum of the first n xi tildes, and you can correspond you can define a corresponding n tilde of t for this truncated renewal process. We have Sn tilde is, what is the relationship between Sn tilde and Sn? See, the xi tildes are smaller than or equal to the original xi's. So, Sn tilde, the nth arrival epoch in this tilde process should be lesser than or equal to Sn, correct. Okay. Now, what can you say about n tilde t? So, in the tilde process the arrivals happen sooner or sooner or later? They happen sooner, right, which is why the epochs are smaller. So, if the arrivals happen sooner, then n tilde t must be, there should be more arrivals at a particular time, right, because some of these random variables might have been truncated, right. So, in fact, between the using the equivalence between Sn and Nt, you can prove that all right. Because if Nt is greater than or equal to n, then Sn is less than or equal to t, which means Sn tilde is less than or equal to t, which implies n tilde t is greater than or equal to n, right, correct, right. So, there should be more arrivals in this tilde process. So, I have some kind of an upper bound going now, right, Nt is upper bounded by some other thing. So, this is great, right. So, limit t tending to infinity, expected Nt over t is less than or equal to limit t tends to infinity, expected n tilde t over t. This has to hold. This is true for this relationship is true for every t. So, it has to hold in the limit, correct. Now, you do the same Wald trick. Okay. So, you have this guy, right, expected n t over t is all this this equation, right. So, you copy that down with the for the tilde process. Okay. This is equal to S tilde so, this here I have to write expectation of x tilde. See, I am using this equation out here, right, for the tilde process minus. So, this I will get minus 1 over t, correct. This is again true for all t greater than 0. Now, what is the saving grace about this tilde process? For the tilde process, the s tilde n t plus 1, right, n tilde t plus 1 is at most t plus b, correct. If you go back to the picture for the tilde process, this gap, see the previous arrival occurred at t or before, right. So, the next arrival, this gap cannot be larger than the largest possible inter arrival time in the tilde process, which is b, correct. So, here it is controlled, the tilde process has been controlled, right, it is truncated. So, this I can say is less than or equal to, I can just keep this limit t plus b over t expectation of x tilde, right, and this guy of course goes away, 1 over t goes away. This maybe I can just write it. So, I do not know why I am writing for all t greater than 0, I am taking limit t tending to infinity, right. So, there is no for all t greater than 0, I just get rid of that. So, what is this equal to? T plus b over t goes to what? 1, correct. So, this guy goes to all right. So, I have an upper bound of 1 over expectation of x tilde. B is fixed. This is true for all B fixed. Okay. So, this much you will agree. Now, it is useful to think of this x tilde as being indexed by B. Basically, x tilde B is just minimum B comma x, all right, and as B increases. So, we have x tilde B increases monotonically to x, right. So, by the monotone convergence theorem, we can assert that expectation of x tilde B converges to expectation of x as B tends to infinity, right. So, in this inequality, right, that expectation of n t over t is less than or equal to 1 over expectation of x tilde B for all B fixed. We can send B tends to infinity, and as B tends to infinity 1 over expectation of x tilde B will converge to 1 over expectation of x, all right. So, 1 over expectation of x is also an upper bound on expectation of n t by t. We have already showed the lower bound. So, which proves the elementary renewal theorem.